Alright, let's check out this example here. So here we have the formula CNO minus, and the textbook slides came with these three structures on here. Is there any different structures that you guys think you would try to draw as Lewis structures that seem like they're more reasonable than these three? So I would say that these three are probably not the most reasonable ones to draw, given that carbon is to the left of nitrogen. Its electronegativity is going to be lower than nitrogen. You probably would start by putting the carbon in the center. Not the nitrogen. You should be able to come up with a more stable structure that way. So if you do that, you have 4 plus 5 plus 6 plus 1. That gives you 16 valence electrons. So far you've used 4, so we've got 12 more. You want to start by putting those 12 on the more electronegative atom. Then we still have more, so we put them on the second most electronegative atom. That uses up all our electrons. So the carbon still needs to make a noble gas configuration. So now you have to think about the different ways to share these in. So does it make more sense to start sharing electrons from the nitrogen first or from the oxygen first? Nitrogen. Why? It's less electronegative. It's more willing to share. So I would start by taking a pair here, sharing it in. Now the carbon has 6. Around it, it still needs 8, so I would share another from the nitrogen. That to me seems like the most reasonable structure. How do I check that though? Look for formal charge, right? If I've got a lot of unnecessary formal charge, I want to think about how I could rearrange things. So for the nitrogen here, its formal charge is going to be 5 minus the number assigned to it. It's got 2 lone pair electrons assigned to it and half of the 6 shared. That's 0. That's great. Looking at the carbon, carbon's got 4 that it needs to be balanced. We're assigning 0 lone pairs and half of the 8 shared. That's also 0. Wonderful. The oxygen in the structure I drew needs 6 to be balanced. Here I'm assigning 6. And half of the 2 shared, that's going to give me a -1. I can't avoid that though when the overall charge is -1. I have to have a -1 formal charge somewhere. The fact that I have it on the most electronegative atom is good. The more electronegative the atom, the more it attracts electrons, the more likely it is going to be the one to end up with extra electrons if there are extra electrons. So this is the best structure I can draw for this. The structures that the textbook put on this slide are by far less stable, and we know that because we can calculate the formal charges for them as well. So if I want to look at this carbon here, it's got too many electrons around it. It only needs 4 to be balanced, and already it has 4 lone pair electrons assigned to it individually, and it's got 4 shared, and so half of those are going to give it a -2. That's a lot of imbalance in one area of the molecule. We already said that a negative or a +1 is unstable, but a negative or a +2 is really unstable. And especially when I put a negative charge on an atom like carbon with a relatively low electronegativity. It's got a mid-range electronegativity, but compared to a lot of the other nonmetals, it's lower than them, and that's not going to be very stable to make that an area with extra negative if it's not an area that can naturally attract negative to it. If I look at the nitrogen here, that's going to be 5 minus, it's got 0 lone pairs and 8 shared electrons. That's going to give it a +1. Again, not very stable to have an unnecessary formal charge. Looking at the oxygen, you'll find that it's neutral. If we look at the central structure, you can apply the formula again. You'll get a negative here. Again, another positive for the nitrogen and a negative here. And then the structure on the far right, just looking at this carbon, it's going to be 4 minus. Here we've got 6 assigned plus 1 more. That's a negative 3. So what is the relationship between these three structures? The relationship between them is that they are in resonance, or resonance contributors. Because I can, when I connect the carbon on the end and then the nitrogen in the middle and the oxygen on the other end, I can get from this structure to the next just by moving electrons around. Right, so to go from the structure on the far left to the middle one, I've got to move one of these lone pairs in to make a triple bond and move one of these pairs of electrons out to make a third lone pair on the oxygen. If I can make the structure into the other one just by shifting lone pairs and double bonds, that's resonance. So then to get to the last structure from the middle one, I'd have to move 2 of these out and 2 of these in. I can do that. So when 3 structures are in resonance, I know that none of them actually exist. What exists is the average or hybrid. But the average will look more like one of the individual contributors if one of those contributors is a lot more stable than the other. And so that's the situation I have here. Well, because these 2 are definitely way more stable than the one on the right. Because here I've got extra formal charge that's totally unnecessary. Here, I've got 2 negatives and a positive, 2 negatives and a positive. They have the same amount of formal charge. Not much of a difference, except I've got extra concentrated negative in one area. That makes it a little bit less stable. So the middle structure of those should be the most stable structure I can make if I put the nitrogen in the center. But we can also see if you have a lot of formal charge, you want to think about other options for the skeleton of the molecule. So if you were trying to draw this formula and you came up with this and you say, this is the best I can do, it's not the best you can do. You want to think about, if I've got too much negative here, I can't get rid of it. What if I were to switch the carbon and the nitrogen position? Here I've got too many electrons, here I don't have enough. So I'll put the nitrogen over here where it has a lone pair to itself, and the carbon in the middle where it's more sharing. That will produce a structure with less formal charge. And that should be the best structure for that formula. Let's look at the one we finished class with last time. So here we said there were a number of structures we could draw. This one was tricky because the carbon and the sulfur had the same electronegativity, so I didn't really know which one should go in the center. So there were a number that we came up with. We came up with a couple with the carbon in the center that make complete noble gas configurations, and we came up with a few that had the sulfur in the center that all had noble gas configurations. So now we can point out that these 3 are all in resonance. So really, if the structure did have the sulfur in the center, none of those 3 would really exist. What would exist would be the average. And these 2 are also in resonance, and I can draw a third one if I want with the triple bond on the right-hand side just to complete the 3 resonance possibilities. But remember, resonance is a stabilizing thing. So if I've got one structure that is clearly superior to the rest by a large margin, the other possible resonance contributors are not going to be very significant, and the resonance is not going to be very significant. Right? The resonance will only be significant if the structures are at least similar in stability. So what I need to do here to distinguish what the most likely structure is to look for formal charge. Right? So I would use that formula So I'll just look at this one. I'm not going to do it for everyone because it just takes too much time, but for the first sulfur here, it needs 6 to be balanced because it's in group 6A. I would subtract from that the 2 it has as a lone pair and half the 6 shared electrons. That's going to give me a +1. So already I'm finding maybe that's not the best structure. This sulfur down here would have the same arrangement. The sulfur on the right, we'll call that sulfur 2. Write it down here. That one needs 6 valence electrons to be balanced because it's in 6A. I can subtract from that 6 from the lone pair electrons and half of the 2 shared. That gives me a -1. So this has the same arrangement. So any sulfur then that has 3 lone pairs and 1 bond is going to have a -1. And any sulfur that has 3 bonds and 1 lone pair is then going to be a +1. So I can start to see where if there are structures that have a lot of formal charge, that's not going to be stable. From the last slide, we showed that a carbon with 3 lone pairs and a bond like this one here is going to have a lot of formal charge. So that has 1, 2, 3, 4, 5, 6 electrons assigned to it from here, plus 1 more from the bond. So that's going to actually be a -3. So that's really unstable. If the carbon has 2 lone pairs, it's a -2. If it has 1, it's a -1. So I can see that the structures on my molecule on the right are not very stable. Plus, when I calculate this sulfur in the center, using the formula, I get a +2. So this is an illustration of why how I can recognize that I do not want the sulfur in the center here. It creates a whole lot of unnecessary formal charge. And so the best structure is this one. No formal charge. This one with no formal charge there on the center left is in resonance with the one above it and the one below it. But since those create unnecessary formal charge, the one with no formal charge should be the main contributor to the average and the major contributor, so the average will look pretty much just like it. So the resonance there is not going to be very significant when it creates an unstable resonance contributor. When there's only one stable contributor, that's what the average or real structure will probably most look like. All right, so another example, CH2O. This is formaldehyde. Formaldehyde has 1 carbon, 2 hydrogens, and an oxygen. There's really 2 ways you could think about connecting the skeletal structure. Then we would count up the number of valence electrons, and we would get 12. So we've used 6 so far. We've got 6 more. Put them on the most electronegative atom first. Then put them on the second most electronegative atom. In the structure on the right, I would put all 6 on the oxygen to begin with, since it's the most electronegative, and in that case it can hold more lone pairs since it only has 1 bond to begin with. Then I would see the carbon doesn't have enough electrons, so I would start sharing more with it in both of these structures to give it a noble gas configuration. So the first thing I look for is to draw the structures that have complete noble gas configuration.
It could be either in those 2 forms, the straight line or the cross.
Yeah, either one is reasonable, but they're not equally reasonable, and the way I distinguish between them is by calculating formal charge. So in the structure on the left, I would calculate a negative and a positive. That's probably not ideal. On the structure on the right, there is no formal charge. That is the correct structure for formaldehyde. Formaldehyde has a carbon-oxygen double bond, and the carbon is connected to both hydrogens. That's the only way to connect those atoms without creating any formal charge. So if I did have this molecule floating around in space because of the formal charge, it's not very stable. It's going to start undergoing reactions. It's going to start colliding with other molecules and rearranging the electrons until it produces something that's usually going to be more stable. Not a lot of molecules around with formal charges on carbons and oxygen. because they're unstable.